So a warm welcome to you all. This is our first regional meeting in spring. So for those of you who observed Spring Day yesterday, we want to wish you a warm and happy spring. I saw a nice quote which said, "Spring will come because it's raining outside." I'm in Cape Town, and so will happiness. So hold on, life will get warmer. For those of you who don't know me, my name is Arlene Volmink, and I'm the president of the ISACA South Africa chapter. I am standing in for Robin Williams today, who is our Western Cape and Eastern Cape Regional Director. He was meant to MC this meeting, but he lost his voice. He is on the call, so I'm sure he'll post a message in the chat as well. So just in terms of the agenda for today, I will do the welcome and announcements. Then I'll hand over to our guest speaker, who is Keith Makan, and he will speak to us on the topic of symbolic execution and its security application. Following this, we will talk to you a little bit around our journey with SACWA and the application and our current progress, and also give you an opportunity to ask us questions. This will be presented by myself and Edmore Taruvinga, who is our Academic Relations and Education Director. And then Edmore will close the meeting. The meeting is scheduled to close at 6:15. But Eskom has its own timing, so we are going to try to close by 6 o'clock because of the load shedding schedule. So just to kick off, I thought let's look at September and see what the month of September signifies. So let me just read a bit to you. It says September is the 9th month of the year in the Julian and Gregorian calendars. It's the third of 4 months to have a length of 30 days, and the fourth of 5 months to have a length of less than 31 days. Some more, it says September is from the Latin word septem, 7, and it was originally the 7th of 10 months in the oldest known Roman calendar, the calendar of Romulus. So now I want to offer a prize from our newly launched ISACA shop for the first person to post in the chat what day of the year the 2nd of September is. So of 365 days, what day of the year is the 2nd of September? I also just want to mention, as I have, that September is the start of spring. Not technically, but let's go with that. The birthstone is sapphire. The birth flowers, I'm a flower person, as you can see with my background. The birth flowers for September are forget-me-nots, morning glories, and asters. And the zodiac signs are Virgo and Libra. And then I just noticed that today is also, they call it Office Administrators Day on Wikipedia, but I think in South Africa it's better known as Secretary's Day or Secretarial Day. So I think it's a nice time for me to acknowledge our office staff who work so hard in the background to present these events to you. So Angr Feldman, our Marketing and Events Coordinator, you'll probably see ISACA SA chapter in the chat. That is Andy, as well as Esther van der Walt, who is our office manager, managing things in the background, and then Eugene May, who is our training and education coordinator, looking after SACWA administration. So I just want to acknowledge them today and appreciate them for the work that they do for the ISACA SA chapter. Right, so announcements. Right. Let me see if I can do this. So the first announcement is around the conferences for 2021. Many of you have attended our recent conference in August last month, where we had a theme of thinking digital. Next year we are offering 2 events, one in June and one in August. So the one in June will be an online event, The one in August will be a follow-up event in person. And the two conferences have a connected theme. So the one is adapting in changing times and the other is prospering in changing times. It will be offered at Empress Palace in Johannesburg. So if you'd like to sign up early and take advantage of our super early bird rates, then you are welcome to make contact with the office. I also, just want to acknowledge the directors who are on this call, because it's through the directors and the office that we are able to plan and arrange these big events for your benefit. Then in terms of upcoming workshops, we have a workshop planned at the beginning of October, with October being Cybersecurity Month. We have a workshop with international trainer John Tannehill, and it will be offered over 4 days with 4 hours per day. So this is a nice opportunity as well for you to get content and background information in order to write the Cybersecurity Audit Certificate exam offered by International. We've also kept the cost quite low so that, during this period we are observant of the financial circumstances in the country, and we're still catering to members' needs. Then we have our Members Awards. So we've extended the deadline from the 31st of August to the 25th of September. And here we encourage you to acknowledge what you are doing within your environments. If you have created an RPA solution, or you are working on some kind of AI project or anything innovative, or you are or you want to acknowledge someone who has really made a contribution to the profession, then please do nominate them for chapter awards. The take-up has been really low so far, so it would be good to get some good nominations. The conference committee will deliberate on the nominations, and then the award winners will be acknowledged at our online member awards event, which will take place on the 30th of October. This was also an in-person event, but due to current circumstances, we had to move it to an online event. Right, and then we have Community Day, which is the second Community Day offered by ISACA International. So what happens is ISACA's 240 plus chapters across the world contribute towards social good on this day. And we have selected 2 initiatives for Community Day, and we encourage members to volunteer their time and to get involved with these initiatives. So the first one is an online workshop aimed more at younger members from 9 to 1 on Saturday the 3rd of October. And we'll be telling you more about our scholarship program, our mentorship program, and so forth. So I encourage you to register for that event. That's just the agenda. Okay, and then on the 3rd of October as well, so this is the fun side. So we said, okay, serious, we'll do cybersecurity. And then on the fun side, we'll offer what we called the Kitty Cat Run. So Kitty is actually the name of Esther's cat. And so this initiative is named after our latest addition to the ISACA family called Kitty. And we have a few ways in which you can get involved. You can drop off donations of pet food at the ISACA office in Johannesburg or at the ISACA office in Cape Town. And we have selected a organization called Kitty Puppy Haven, where we will be donating those items on the 3rd of October. We are also running a My Pet and Me competition. So if you want to take a photo of yourself with your pet, then you can post that to us, and we will have some nice prizes as well to celebrate Community Day. The pictures on the right are beautifully taken pictures from Kitty in Citrusdal. And you can see a nice one with Kitty with some pink flowers in the background. All right. And then just lastly, in terms of announcements, we've launched our online shop. So there's many items for sale, and you're welcome to have a look. They're all ISACA branded items, ISACA South Africa chapter branded, and offered at very competitive prices. So that's all in terms of our announcements today. I hope I've done a good job, Robin. All right, so let me introduce our speaker, Keith. Keith is a security researcher and consultant with 7 years of experience in the field. He's worked in countries across the world and as a consultant at the biggest software companies on the planet, including FANG companies. You'll have to tell us what that's about, banks and various other industries. He is currently working on his master's focused on symbolic execution applied to automated vulnerability detection. So on this note, I'd like to hand over to our guest speaker, Keith Makan.
Yeah, by FANG companies, I mean, I just meant like big businesses. I've helped people like Google, people like Amazon, a bunch of folks. I've been sort of involved with pretty big businesses, helping them read code and make sure they don't push out insecure products. But yeah, I just meant to talk about a little bit about my experience. But anyway, let's get into it. Who am I? My name is Keith. I wrote 2 books a little while back. One of them was the Android Security Cookbook, and one of them was penetration testing with a bash shell. Basically, they're sort of focused on sort of more practical assessment techniques, what you should look for in apps, especially Android apps, what you should look for in the OS to find vulnerabilities. The penetration testing with the bash shell book was about how to bash script so that you can get penetration testing activities done quicker. But yeah, I've also, as Aline said, she's basically finished the slide for me. For the most part, I have about 7 years of experience. The synopsis of my job is to tell people that their tech, their setups, or their code is bad, and they pay me money for that. I'm currently working towards a master's degree, and right now I do like freelance assessments whenever my supervisor leaves me alone, basically. So yeah, and sometimes I blog about the odd experiments and things I learn. But yeah, so what are we here for? Essentially, there's a new technology that's becoming really popular, and I'm going to talk about what it is. I'm going to explain a little bit of the basics of what symbolic execution is. We're going to walk through a simple theoretical example so that everyone has sort of a grip of what we're talking about and can kind of picture how certain technologies are designed and how it correlates to actual code and actual technology. We're going to talk about some of the drawbacks and some of the applications, and then at the end I'll introduce a Python framework for actually getting stuff done, making use of symbolic execution. So that if anyone wants to, take this further than just a discussion or just some general knowledge on some new tech, they can totally do that. So let's talk about what symbolic execution is. It's been around since about the 70s, and for the most part, it's an extension of sort of fields in computer science and formal maths. I'll talk about how it's an extension of maths in a second, but it's been around since then. Way back when, before we had powerful computers, it was pretty much just a sort of a good idea of what should be done to formally reason about programs. So if you want, this is a way for mathematics to prove what's possible with programs. And it doesn't only apply to programs, it applies to anything that's going through or has to be computed in some way. Only recent times, and by recent I mean 10, 15 years, the last 10 to 15 years, people have really been pouring investment and pouring sort of academic and industry attention to it to actually try and solve security problems. And this is primarily because we now have the compute power, the clouds, the very beefy desktops that can actually run the analysis. So that's the reason it's becoming popular now. It's not that we suddenly realized that it can apply in some ways. I think people always knew it was very useful, we just didn't have the muscle to get it done. To start off with, let's say it's a static analysis method, even though, speaking from a sort of strictly academic description, it gets blended with other forms of analysis, but if we're talking about symbolic execution on its own, it's a static analysis method. And what that means is it takes in programs or descriptions of programs or descriptions of software, and it doesn't need to run them in order to produce the results of its analysis. So it doesn't need an environment, it doesn't need to actually execute it on hardware in order to produce conclusions and reason about software in a useful way. So one of the taglines people like to talk about when they talk about symbolic execution is it runs input under symbolic input instead of concrete one. So that means it doesn't give, in order to find out what software does, what states it'll take under certain input, it doesn't need to give it actual examples of input. And it's very useful because it can sometimes take a long time to work out exactly what kind of input a program wants. So you think about things that like process USB packets, or things that process Bluetooth frames, or things that take in configuration files. Things that try to brute force work out how to make those programs tick can take a while. These methods do not need to rely on that. It guesses the input in another sort of clever way. The result of symbolic execution is to show you obviously what a program can do under certain inputs. So you want this map of type of inputs to the states that the program can take, and we're going to see how that is super useful for a lot of reasoning about software. It employs SAT and SMT solvers, so I'm not going to launch into SAT and SMT theory to a great extent, and you can think about symbolic execution keeping that opaque to a large extent. But just to give you a little bit of background, SAT and SMT solvers basically are ways to approach what's called the Boolean satisfiability problem, and that's basically a problem in mathematics that focuses on finding solutions to Boolean equations. So everything we're doing here, everything we do with programs and language in symbolic execution boils these statements down into Boolean equations. So there's simple relations of yes or no values, and I don't know if you can see my mouse, but sorry. Oh, you can see the bottom two statements here, proof theory. There's a V, B, V, C. That's like A or B or C. Those are essentially sentences that are strung together, made of purely Boolean relations between constants. And this SMT and SAT solving business is to produce efficient and quick solutions to those equations. The reason we like that is because mathematics and proof theory have developed a lot of tips and tricks to reason about these kinds of statements in procedural ways that we know will or definitely won't produce some answers. So it's just taking all of that procedural solving theory for these kinds of equations and employing it to reason about programs. So obviously you have on one side Boolean equations that have a configuration of yes or no answers, on or off, 1 or 0 answers, and you have on the other side programming language, which is reasoning about integers and arrays and strings and classes and all these complex things. And symbolic execution basically bridges the gap between these two descriptions of programs to reason about what they'll do. I hope that's very clear, but all you need to take away is that there's complex language for things. It gets boiled down to Boolean equations, and then it gets shoved in an SMT or SAT solver, and that churns out answers to what we'd like to reason about. And this is an old game in formal proof theory and mathematics. Essentially, the whole field is about how to rewrite statements so that you can reason about them in procedural ways and conclude things about their properties and the larger sets of values that they describe. So let's look at a simple example. I'm hoping C isn't completely unknown to everyone, but you don't need to be a C expert to get what's going on here. We just have a simple if statement and a program that takes in two integers from the command line. So basically it takes in two values from the user, and it says, look, if one plus the other one is bigger than 10, set a value for X. If not, set another value for X. And it's a simple example, but obviously programs kind of recursively reuse a lot of definitions. So you might have this example compiled into itself, you know, ad infinitum, or like tessellating down into many levels. You could have the same situation repeated in more elaborate, even more simple ways. So this does represent a lot of what goes on. But to start off with symbolic execution, just in a theoretical sense, we need to describe a symbolic state, and we need to relate symbolic states to each other. So the first thing we do is you have an initial state, and in the symbolic state you need essentially 3 or 4 things. Some more academic descriptions of this thing, of this style of reasoning, can be a little bit more full of nonsense about what you need. But as far as I've learned, you basically need these 3 things: a variable store, a path condition, a program state when you're modeling, and to differentiate the different states, you could have a little state label or state number, and this is essentially what it looks like. So our first statement doesn't require. So first of all, the path condition. We just start there. Path condition is very important. It shows you what needs to be satisfied in order to reach the statement we're modeling. So because we're modeling the first couple of statements, we don't need to satisfy anything. Nothing needs to be true or false about the input in order to get to the statement. So the path condition is true. It's complete tautology. And the variable store, just to make things simple, I've started off the initial state taking in symbolic values for the 2 variables we have. So what you see is X takes on A and Y takes on B. A and B are symbolic variables, and we will treat them as though they can take on any input throughout the analysis, and we'll see how that happens. So now we've modeled these first 3 statements, and again, I should warn you, this is a huge simplification of what's happening here. The actual function A to I that takes in this array index, it can actually be pretty complex to execute symbolically. I'm simplifying it and skipping it in analysis here because it doesn't really bring anything to the table as far as the example. But if you were actually modeling this in a symbolic execution engine, that function would give you quite a bit of headaches because it actually does do a lot of checks on the input. But yeah, so now enveloping the if statement from line 4 to 6, obviously we have the initial state, and from that, because the if statement can fork off in 2 directions, it can either have a true execution path or a false one. We now have 2 more states that follow from our initial state, and the state number 2, as you can see, is the statement 5, which will only get executed if the if statement is evaluated as true, which means the path condition will be whatever gets you to this statement, and that's if A plus B, which is the symbolic values of X and Y, are bigger than 10. The other thing you can see here is that the symbolic store, the variable store, is updated because we've now done something to X and Y. And this is important because going forward, you obviously want to include in your reasoning all the changes that happen to the variables, and you want to envelop all the things that might affect the values required to reach certain program statements. The other side, we have the false side of the if statement, which means that A plus B is smaller or equal to 10. And then obviously it modifies the variable store, including this the thing that happens to X, and therefore the symbolic value A. This is a simple example. Now if you take this to a stat solver, basically what you do is pull out the path conditions, and we can then ask it what needs to be true about X and Y in order to get to statement 2, what needs to be true about X and Y in order to get to statement 3, and the way it'll do that is it'll convert the path condition into a Boolean equation that the SMT or the stat solver can give you values for, and obviously the values would fit whatever constraints are applied to the actual inputs. But this is the basic example. What happens now in a more elaborate sort of situation is you would have maybe state 2 or 3 represents some kind of property you want to get to. Maybe it represents a point in your program that doesn't require a password to get to, doesn't have enough entropy to generate random numbers for cryptography. Maybe it represents a firewall setting that you can get to that shouldn't be allowed, etc., etc. But this will be elaborated by actually looking at the path conditions that are imposed on inputs. So yeah, how do you actually produce this kind of reasoning? So what we did here is look at a very theoretical example, and there's all this variable stores and path conditions going on. What do you actually do in terms of the process? And I know this is going to involve like a little bit of computer science and some things that I'm not going to completely unpack, but if some of you have done compiler theory before, you'll find these things familiar. But anyway, the basic process is you have to take code, and just like any compiler or any sort of formal reasoning about code, you eventually would have to end up with some kind of syntax tree. And syntax trees aren't very scary, they're just another way of rewriting the relations between operations in code and the inputs that it takes. So we can tell when one input is related to a function call further down the line, it'll be reflected in the function tree, in the abstract syntax tree. It also presents a very nifty form that can be converted to and from different forms and keep the same reasoning, the same relations between values and function calls and activities on the variables. To get to the place where you have symbolic states, you essentially take the abstract syntax tree and you convert this into a bit. You convert this into bitwise operations, and the reason you want bitwise operations is because you want to be able to convert that into constraints and basically Boolean equations. And obviously, the SMP solver, as I've mentioned, or the SAT solvers, don't know what integers are. They don't actually know what an array is. They don't know what a class is. They have no such complex like representations of information. All they know is if you give me something that I can convert into, equivalently a truth table, I will be able to reason about it. But to get things there, we take an integer that we're dealing with, and instead of dealing with a concrete integer, we convert that into a field of bits. So as many may know, in a computer, things aren't represented in some of the intuitive number formats that we know. All the computer knows is on or off values. To a certain extent, a computer is just a big Boolean equation. And to kind of encapsulate that in reasoning, we represent the values that it reasons with as bit vectors. And they're just fields, they're just an array of on and off values that are as wide as the integer values we're trying to reason with. And I say integer because it's kind of the base form of a lot of things, but that integer could be an index in an array, it could be a number for a setting, it could be anything. But you basically take the nice, neat, encapsulated data formats that you have that the programming language forwards, and you convert that into bitwise equivalents, and you can take the bitwise equivalents and convert them into constraints. And once you have constraints and how the constraints related to each other, you can essentially stitch together symbolic states. And what happens with the symbolic states is much in the same way that emulation sort of recreates an environment around a program. So the symbolic, to model a symbolic state, you need to envelop also the kind of implicit activities that things like computer registers, sort of like all the CPU registers would have effects on the values. You might have CPU flags, you might have memory values that actually affect computation. All of this needs to be nicely, neatly packaged into your symbolic state, depending on the accuracy of reasoning you'd like to get to. But essentially, the process is you're going from code, from the code, you have an AST, and then everything from that point is just mapping the AST constructs onto things that allow us to reason a bit more accurately. And I know there's a whole bunch of jumbled words if you're not used to hearing about this kind of stuff, but essentially you just map AST statically into other concepts, and obviously envelop whatever implicit registers or value stores the machine will have along with it. And once you have the symbolic states and the relations between them, you can then perform reachability, what's called reachability analysis, which shows under certain inputs, under certain, as we mentioned, under certain values, what states can be reached. You essentially build a little database that you can search through based not on static inputs, but on input forms, which means it's quite powerful. And the other thing I should mention is because we're working in sort of bitwise, bit vector terms at some point, it means that the process that you're developing for symbolic execution to some extent can also reason about hardware definitions. And one thing I didn't mention is people who verify the correctness and who produce formal proof for whether hardware will operate correctly also use symbolic execution and constraint solvers to determine what's going on. So if you design some kind of circuit, you're some kind of electrical engineer, you design a circuit that adds numbers, let's say, and you want to know whether it's possible to add numbers in some sort of way that will go awry. One thing you might be doing is producing some kind of representation of your circuit that would be friendly to a SAT solver, and this eventually would mean converting what your circuit does to bitwise or bit vector equivalents, turning them into constraints, and throwing them at a symbolic sort of reasoning engine. So a very, very powerful form of analysis, because it can not only take sort of theoretical code, these abstract forms that we deal with in code, it can actually model something right down into the hardware if you really tried. So that means you can have a view of basically everything the computer should be doing. The only drawback here is you need a lot of computation power to keep all of that stuff in tandem and make sure reasoning is as hairy and as detailed as possible. So looking at some of the sort of concrete security applications people have had for this, there's a lot of examples in this field, but I thought I'd pull out one of the sort of most novel ones, one of the ones people would be talking the most about. And deep fuzzing is one of them, especially Driller, which is something created by the team who actually produced the Python framework I'm going to talk about in a second. But essentially, some of you may know what fuzzing is, and fuzz testing is essentially a way of brute forcing test cases for programs in a certain way that throws different input values at a program until it hits something that reaches or uncovers a certain execution path in the program. So you, for instance, try different inputs in different ways in order to uncover execution states in the program, and you would do this optimized to uncover as many execution states as you can. So for instance, if you're fuzzing against something that adds numbers, you would throw numbers at it until the way you've instrumented the program shows you're actually discovering new execution paths. But the problem with these fuzzers sometimes, it's a common thing, they can fall into what's called a hill climbing problem. So you fall into a state where you don't really know whether there's a point to actually increase your coverage or whether you've actually hit a max. And this happens because they don't have a good view of the whole branching space of the program. I'm just checking on the chat because I need to make sure everyone can still hear me. Yes, I will be taking questions. If anyone has any questions, I'm happy to explain anything. Just try to follow for now and write down whatever you'd like me to clarify at the end of the talk. But yes, so fuzzers are great. They can find things pretty quickly if input spaces of a certain kind, but they can get stuck. They can obviously get stuck in the complexity of input, especially if you have, again, things that work on Bluetooth packets, things that work on system core formats. They can be very complex, and to brute force all of this data may be kind of not worth it, because you would have to try a lot of values before the obvious format of the input is possible. As you know, things like Bluetooth packets and USB packets have a certain format, and the entropy in this format is isolated to small places in the input format. So if you really want to be efficient about fuzzing these things, what you do is have something that lets you know where this entropy is, how much time to spend on different parts, and this is exactly what Driller does. It uses symbolic execution to guide fuzzing towards parts of the program that are going to be more interesting and involve more complex input. And the way it does this is by using kind of an analogy of the program that there are certain components that are unearthed during fuzzing, and if a fuzzing engine, like the one it uses called American Fuzzy Lock, if it gets stuck in a certain component, it pulls out the path constraints that I showed earlier and tries to mangle them to produce input. It actually does a very simple thing. It flips it to try and produce input that moves beyond whatever branch it's stuck on. But the point being, it employs symbolic execution with its view of the branching nature of these states and the path conditions that govern this branching to actually guide it towards more interesting parts of the program, so it doesn't only hit one part, because you will eventually realize that you've tried, on a whole input space and you're not getting any crashes, and it gives you a way to move beyond the point. The other thing that symbolic execution is super, super useful for is vulnerability discovery. So as we talked about, this is sort of in the field of deep fuzzing, but vulnerability discovery kind of can happen on purely static analysis basis. Sometimes you want to find vulnerabilities in things without actually running things. Maybe it's code or software that you don't have the environment for, or that's too complex to set up. And this is especially true for embedded firmware. So if you have yes, fuzzing is legal. If someone asks me that, it's not only is fuzzing legal, this is a little bit of distraction, but for instance, the browsers you're using, if you're using Chrome and Firefox, they're basically being fuzzed 24/7 by AI, by massive like infrastructures. Google has a whole cluster that dedicated to fuzzing it, and they actually invite people to submit bugs. And most of the bugs that people submit to Google and to Chrome, to Chrome and to Firefox, they're found by people fuzzing Firefox. And actually, if you want to get into fuzzing, totally do, because it means you'll be able to find problems in the software you use, and you get a good picture of how trustworthy it actually is. But coming back to vulnerability discovery, basically, you want to reason about these things. These programs, they can be pretty complex and hard to emulate. But the basic process for involving symbolic execution is you would start with something like a static analysis. And by this, I don't mean you start with symbolic execution. I mean, you look for, in very simple, very straightforward, sort of linear ways, you look for points in the program that are identifiable through string matching, through certain signatures, layouts of code. When you start with a light static analysis process, as it's called, it's usually just looking for certain strings or naming conventions in the program to help you decide which parts of the program you'd like to target. And as you look at the example, the little diagram I have here on the right, this target is meant to represent that this program has been put through a static analysis process, and this one section of the program stood out, and the process is actually moving through analysis to try and see if there's a way to get to that point. And after symbolic execution, it actually find out, okay, if f of I and g of I, which are functions on the input, are true, then you can get that point. And having this means you now not only can show that the program will get to that point, you can actually produce the input that would get you to that point because of how symbolic execution works. But some novel examples of this is a project called FirmUSB. I've included links to the papers that describe these projects and walk through a lot of detail on how they work at the end of the slides. But FirmUSB, basically really cool. They basically use static analysis to find out if there are USB descriptors in firmware, and a USB descriptor is essentially something that USB firmware, like on your flash drive, on your hard drive, anything that's connected to a USB cable and is serving something in your computer, it needs to eventually spit out like a series of bytes that says, hey, I'm a USB thing and I can do these things. It eventually gives it some kind of service description so your computer knows what it does. But the problem here is that they can obviously betray that description eventually. So something called bad USB, which was an attack someone kind of modeled, I think it was at a couple of security conferences, but bad USB is essentially a USB device that will present itself in one way, like a USB storage, and then suddenly switch to a different kind of functionality once it's trusted by the computer. So you can have something that says, I'm a storage device, and then later on goes, okay, actually I'm a microphone now, and then starts recording all the things and your keystrokes and things like that. It can be pretty bad if you don't actually pay attention to what your devices do. FirmUSB is essentially looking for that kind of behavior by checking if certain parts of the program have descriptors that can, and it does this by showing, okay, you have reachability to one part that has descriptors, and you have reachability to another part. How can there be two sets of descriptors? Maybe that's a bit malicious. That's sort of the maps of the program, but it does this obviously by employing a symbolic execution because it can give it the power to actually concretely show reachability to these different states in the program. The other cool thing is FirmAlice, and I admit FirmUSB is a little bit more malware analysis, but FirmAlice and FirmUSB sort of seem like twins and go together quite well, especially because of how they reason about programs, so I've included it here as well. But yeah, FirmAlice, really cool idea as well, and especially again for embedded firmware. This is a common problem with router firmware. You have a lot of people who build routers and don't really put them through as much strain, and this is not a thing that sort of spans across all router manufacturers. There are definitely some who spend the time and the budget looking at different ways to secure their devices, but there have definitely been, especially in the IoT space, I'm sure people in the field here have heard all the horrors of IoT security. One of the common things is that they have what's called authentication bypass vulnerabilities, and the synopsis of this kind of problem is that you can get to an authenticated action without requiring authentication. So for instance, you'll have a nice little login page for your router, but unbeknownst to you, there's a way to send it a certain request that will actually change the admin password without requiring any authentication. So it'd be really nice if there's a piece of software that you can pull this embedded firmware through to show that there's these kind of reachable states that don't in the program that don't require passwords or any entropy or any input that can protect it to any great degree. And that's essentially what FirmAlice does. It looks at the input paths. It says, look, I can get to this authenticated state, and it identifies authenticated states with static analysis. It says you can get there without any significant protection or complexity of input, which is super useful, especially because it reasons about binary programs, compiled executable formats. It doesn't actually require all source code and all the libraries to be included. It can take in raw formats and just spit out analysis about it. The other really cool thing, and I'm going to have to explain a little bit of what's going on here, is automatic exploit generation. So there's this kind of bug in certain programs, especially when they're compiled from things like C and C++, even though other kinds of programs definitely have them as well. They're called memory corruption attacks. And essentially what happens here is you have the ability to corrupt the data structures, key data structures in something's memory. Some of you may or may not know that in a program that runs on most machines, There's things like heap memory, there's things like stack memory, read-only memory. These things usually have a certain format to them, and if your input, or you can control what's written into them to a certain extent, you may also have the ability then to actually redirect execution completely and make the program do literally anything you want, just from giving it certain input. And this is kind of an unsolvable problem. Primarily, I mean, people have spitballed about why it's so hard to solve memory corruption, why it's so impossible to completely fix it. Some of it has to do with the fact that a program stores instructions where it stores values, and there's no concrete way to decide whether something is a value or an instruction. And there's always ways to fudge the line between the two, depending on the flaw that you're trying to exploit. But that's another hairball to get into. What we should focus on here is that there's sometimes a way to influence the data structures in memory that a program relies on to effect complete control of the program, make it do whatever you want. And one of the ways you do that is by building what's called a ROP gadget, a return-oriented programming gadget. And all this does is it's a way to mitigate protection against memory corruption attacks. So usually what they do to make memory corruption attacks really, really hard to exploit is they randomize where things will be placed in memory every time a program runs. And this means if you're expecting to overwrite certain structures with values that are static, bad luck for you. You're going to have to work out where these things that you want to reuse, or where these things you want to actually control in the program are going to fall in memory at every single run with a certain amount of entropy. And return-oriented programming is great because it means you can now, instead of using static values or literally injecting new instructions into the program, you can just point it to places inside its own instructions, so you can give it its own code to execute that would be chained together in some way to then affect full control. And this automatic exploit generation technology, which uses symbolic execution, actually builds these payloads that you can inject into programs automatically. And the way it does that is it pulls out any snippets of code that it can reuse in a binary, and this is called the discovery phase. It pulls it out, it classifies them into different types because they all do different things with inputs, and essentially a ROP gadget is something that would do a few stack operations or do load a few values into registers and then return. So this is why you see a ret instruction at the end of these examples. The return is important because it returns to whatever the next instruction to execute is, which would again be one of our instructions. So if you imagine chaining up these instructions together, you would have move, do some things, and then return, and then you would eventually have another one that follows that goes pop, pop, or exchange, and return again. If you don't have that, the program's going to continue executing, and then will run amok somewhere because it doesn't have any more well-formed instructions to execute it. You won't be able to control execution in a very consistent way without this kind of stoppage of return instructions that makes it return back to the control points you're injecting. But anyway, point being, you need to reuse the program's own code, and because you're reusing code with a little bit of analysis and a little bit of graph theory, you can actually build a data structure of this code that symbolic execution can reason about to automatically build you exploits of a certain kind. I can get into a little more of the technicalities of how exactly this happens, but the point I'm trying to make is symbolic execution is really, really cool, and you can actually automatically build payloads with this that give you complete control of a program, which kind of makes analogy sense, because if you can reason about a program in such a sophisticated way, there's no reason that you can't reason about the input in such a way that you can control the program itself. But that's essentially one of the ideas that make it really, really powerful. Up till now, this was pretty much imagined as a super manual process where hackers would have to sift through the code and then test little combinations and see if it works and see if your registers will end up with the right value. Now we have proof theory that will concretely reason about what the value of the registers will be when your payload executes and actually produce real input that does exactly what you want. But of course, even though this is very, very powerful, I will get to whoever left the question in a second, or after the talk. But even though this reasoning is very, very powerful, there are some pros and cons. The main problem being state explosion. So you cannot just throw a binary or a program at a symbolic execution sort of reasoning and expect it to go all smoothly. We don't know how to cater to all program forms in the universe. Some of them can be too complex to reason about. And this is also something many mathematicians believe is connected to Gödel's incompleteness theorem. There could be other ways to prove it's connected to deeper problems in mathematics and deeper problems in computation. I'm not going to get into exactly why that is, but essentially you can get programs that are way too complex and forward way too many symbolic states to reason about in a useful way. To get around that, and another way this comes to the fore is memory explosion, which means you have too many symbolic states that even stall to begin like reasoning about. And obviously this sacrifices completeness, this sacrifices soundness of analysis. So if you were coming to the table thinking that symbolic execution always means absolutely formally correct and concretely provable reasoning about programs, sorry, sometimes the programs can be way too complex to do that, and we need to skip corners, which kills some of the confidence in how concrete the reasoning is. But the good thing is it's very powerful. You can affect very deep reasoning about programs. You can reason about programs as a property of the reasoning depth. And when the circumstances allow, when you actually get a little win on the side of state explosion, you can produce the sort of formal, very concrete proof. And obviously one of the points is you get to brag that math actually is super formal. Abstract math is actually very applicable and very useful in a way that's demonstrable to people who aren't as nuts about math as you are. But yeah, so that's kind of it. There are symbolic execution frameworks out there. This is 3 of them. There are many of them that solve smaller problems and cater to different kinds of applications, but the 3 that kind of stand out is CLI. CLI is one of the more invested in academic tools. You can obviously use it to reason outside of the academic industry, but it mostly is geared to acting on source code available programs. You need the source code if you want to use CLI. You need to know C, you need to know C++. Please go to that link if you want to find out more about it. It's pretty much a stock standard heavy-duty research and industry tools you can get, as far as I know. There's also Triton from Quark's Lab. Quark's Lab is one of the groups, one of the companies in InfoSec and sort of hackery things that are on the cutting edge. They're always doing amazing stuff, and they decided to build their own symbolic execution engine. I don't see that many people use it. That's why I say it's the new kid on the block. It's actually not that new. But it is a pretty cool offering. It's got a C and Python and C++, I believe, front end and library and APIs. So you can go all crazy with it in all 3 languages. Angr is the one I'm focusing on. I'm going to show you a quick example before we end. I know I'm almost out of time. But yeah, so Angr is written in Python. The folks who wrote Drill wrote Angr. People use it out the wazoo for CTFs, for competitive security problem solving, basically is what I would call CTF. And it's pretty easy to understand once you get the hang of it, and there are lots of examples to learn from. So that's why I like talking about Angr. So let's say you're presented with a binary that looks like this. So some of you may not know what we're looking at, but this is essentially when you take a compiled executable program and you disassemble it. A lot of disassembly programs like IDAPRO, Binary, Ninja, Hopper, Hydra, those kind of things will give you back a control flow diagram like this. It'll show you the instructions that are in the binary. It'll show you what happens in certain, how to branch. And to a large extent, this is a best effort picture of what the program will do. Programs can obviously be written in hugely obscure ways, so that drawing this graph would probably be very hard. But here we have a simple example, and I'm not going to step you through all the process of reverse engineering it, but if you can read assembly, you'll quickly realize that this takes in the argv pointer, which is the pointer to the command line input, the user input a program will get, and it then passes it to something called check password. Now, I don't have a graph or a plot here of what check password will do. The very important reason is that we don't need it. We can actually use symbolic execution to handle knowing what it does for us. And all we need to know is what marks our win state. So obviously we want to give it the right password. And here we can see that there's a win state that says jackpot. You got it, good, correct. And there's another state completely disjointed from that called fail. And that obviously means you didn't give it the right password. So what we want is we want to give it the password that gets it to end up in the win state. And if you're using Angr, you just need to write this simple program, and it will actually work it out. Quickly running through this, not to get into a lot of detail, but you need to do three things basically to get Angr to give you an answer. You need to load your binary, and that's the first thing you do, load up a binary. Here we can see the binary is called binary.elf. You need to model the actual arguments you're giving the binary, and that's what we're doing with arg equal BVS. The BVS here is bit vector symbolic, I believe the S is for. And we're saying okay, you can make it 0x20 bits, which I believe is 32. You then, once you've loaded up your, once you have your arguments, you have your binary loaded up, you just set up an initial state, as we did in our theoretical example. You set up an initial state so that the simulation engine knows where to start, and once it knows where to start, you're going to tell it where to end, when to stop its execution, because unless you tell it what to do, it'll just keep on going until there's no possible way to execute any more symbolic states. But there's a built-in method called .explore for the simulation engine that you can either pass this an actual block address. So it's going back here. See these green numbers on the left? Those are addresses that in the program instructions, so that you can say, look, simulation engine, just execute everything until you get a state that ends up with one of these numbers. So that gives you the depth of the execution you want to achieve. But you can also give it a function. And the function, if the function, upon being passed a certain symbolic state is true, so it's a function of symbolic state, it will then return. And what we're doing here at the bottom, in search for a solution state, is we're building a function of that state. And we're saying, look, we don't care about anything that's happening in the state. All we care about is if the state causes the output jackpot to be printed. And you can see this here, if jackpot in output return true. Pretty straightforward. That's all it needs to know, and it'll handle the rest for us. You don't even need to know what check password does. And basically to print out the solution, all you do is you tell the simulation manager to look for all the states that it put in the found stash. So this is a stash of symbolic states that are put in a certain group. And if it's in the found state, it's because when it passed the state to the is-successful function, it returned true. And what I do then is here, for all of those states, I just want to see what the arg, the values for arg, which we modeled earlier, would be to get it to that state. And here's an example of us running it. And just some preliminaries. The first couple of commands are just me saying, look, what kind of file is this? It's a 64-bit elf. I try some random password for the solve me binary. This is the one we're going to give to the actual engine. I give it some random password. It says fail. I know we're doing solve me binary here, and in the code it says binary.elf. Just ignore that error for a second. It was a naming error. But anyway, here we can see the action going on. I've got the Angr example.py. I'm giving it the actual binary as an argument. And what happens is it crunches through it. It says, okay, I'm symbolizing a bunch of memory. I have to actually load the binary. I have to do all this stuff. You can see here how many symbolic states it steps through. And once it's done, it actually spits out the string that says run goal 34, which is the actual answer. And when I give that to the binary, it actually prints out jackpot. So we've obviously shown here that like we've taken this potentially very complex function. Who knows what check password was doing? Who knows how complex it was? And all we needed to know was what marks our solution state in order to get the right answer. So hopefully that actually shows you how powerful this reasoning can be. But yeah, that's pretty much it for me. I'm sort of opening the floor to any questions. I suppose I should go through. Sorry, go for it, Arlene.
Okay, thank you so much. I think there are a few questions in the chat. I don't know if you want me to read them to you or if you're comfortable to go through them.
I'll go through them. Okay, so someone said, "Hi Keith, can the authenticated code be corrupted and security settings be bridged in a way or form which could affect security from an audit?" Oh, that's a very complex question. I suppose I see what you're saying. Can someone inject or attack a program so that the authenticated code could be changed? Yes, but the problem we're trying to solve here is analysis based on not a program that's actually running or has been through an attack. We're trying to prevent possible attacks. So we're producing analysis for a program before it's even run to tell whether we can trust it or not. And in that sense, there would be no possible way to reason about corrupted authenticated code. So I hope that answers the question. The next one we have is, which programming languages are vulnerable to attacks or mostly targeted by hackers? I don't think there's a good way to answer that question, because it would super depend on what solution you're using the programming language for. Java has a lot of problems, even though Java can cause huge problems, even remote code execution problems, even though it has, it handles memory for the user. You can sometimes do just as devastating things to a Java program as you can to a C program. People have tried to, at a language level, solve security problems. They only work so far, and it kind of depends on what kind of problem you're trying to solve. So some are obviously suited better for others. Memory safe languages definitely exist. Microsoft does a lot for its C and C++ languages to prevent things like control flow, execute control flow stuff. They try to prevent integer overflows and all kinds of other things. All languages have these sort of built-in reasonings most of the time. They only get so far, and I think the best way to kind of avoid problems of being targeted is to make sure you're sort of reviewing what you're doing and reasoning about your application in a good way. I would love to tell you, okay, this programming language doesn't get targeted by hackers, but I would be lying as far as I can see. Java gets targeted, C++ gets targeted, PHP, C#, all of these things can culminate in very big problems, can cause very big problems if you don't use them properly. Then I have another question from the same person. Which programming languages would you recommend to begin a little more start with? I think Python is a great place to start. Python or Go. And once you're comfortable with that, literally any language that sounds like it'll be fun. I think people should learn one language and start gobbling up as many languages as they can, even if they're not going to use it. Just learn how it works, learn how to get comfortable with it, and from that point choose the languages which you'd like. But a good one to start, I think, is Python. I would immediately recommend Python.
Thank you so much, Keith. So I learned through the great many of in working.
I'm sorry, the audio is breaking up. The audio is breaking up a little bit, so I couldn't get your question.
that relationship working, or that coexistence between IT and ethical hacking.
Okay, can you please type this in the chat because the audio breaks up a little bit? I heard something about a relationship.
Yes, so no problem. Good questions in that out everyone. And yeah, on that note, I just want to, on behalf of Raul and ISACA, for your presentation today, Keith, and your time in preparing the material. Raul sent me a message to say he's speechless.
Oh, that's hilarious.
Okay, thank you so much. I'm just going to share my screen again, if that's okay.
Well, thank you, Aline. Thanks everyone for having me. I hope folks learned something and they have some more things to explore. It was a pleasure delivering a talk to you guys. Keep focused.